Hello and welcome. Introduction. Now in this video, I'm going to show you how to use the GPIO external interrupts to control an LED of the Tiva C series LaunchPad board using assembly language. Okay, before I go any further, let's take a look at what is an interrupt. Okay, so here is a TM4C123G 6PM microcontroller, and we assume that the microcontroller is executing a program, which I will call it the main program. And connected to this microcontroller is an external switch. Now, this switch is used to generate an external interrupt signal. And the interrupt signal is generated when the switch is pressed and released. Now, the interrupt signal generated by the switch will interrupt the main program that is running in the microcontroller. The main program would then be suspended, and an interrupt service routine, an ISR, will be executed. Now, once the ISR is completed, the control is then returned to the main program. Now, please note that the interrupt can be external, like this situation here, or it can be internal. An example of internal interrupt is the one that is generated by the SysTick timer. Let's take a look at the interrupt again, but this time we use this illustration. Assuming that we are running a main program here and an interrupt occurs. Now, the interrupt can occur at any point in time during the execution of the main program. We have no control over when the interrupt occurs. All right, so assume the interrupt occurs at this point. Then the main program is suspended and the interrupt service routine, the ISR, will be executed. Now, once this ISR is completed, the control is then returned to the main program, and the rest of the main program will then be executed. Hey, so this is the Tiva C series LaunchPad board, or the EK TM4C123GXL. Now, I'd like you to take note of these two push button switch here. So this one is SW1 and this is SW2. And the RGB LED is here, but I'm only highlighting the blue LED part. And here is a partial schematics of the Tiva C series LaunchPad board. There is the EK TM4C123GXL. And I'd like to highlight these two switches that we mentioned earlier, SW1 and SW2. And SW1 is connected to PF4. And SW2 is connected to PF0. PF0 stands for port F bit 0, and PF4 stands for port F bit 4. Next, I like to highlight the blue LED, which is LED B, which is this one here, and that's connected to PF2, that is port F bit 2. Now, in this video, what we're going to do is we're going to control this blue LED based on the status of SW1 and SW2. Now, the switches are used to generate the external interrupt. So these two switches will generate the external interrupt. So when SW1 is pressed, all right, an interrupt will be generated and the blue LED will switch on. Now, if SW2 is pressed, an interrupt is generated and the LED turns off. The program full listing. Okay, so here is the full listing of the program that I'll be using in this video. I will just show you the full listing first, and I will explain the details of the code of the program in a few moments. So very briefly, so this is the initialization of the code, and from here, this point onwards, I define the symbols for the registers addresses. All right, from this point onwards, __ main prog, that's the start of the main procedure. As you will see, it is quite a lengthy main program. Very briefly, so here this code, this instructions here basically make port F0 configurable. Then there is the lock port F. Then there is a configure PF2, PF0, PF4, and so on. And this will enable the digital functions. This here will enable the pull-up resistors for PF4 and PF0. And this will configure the edge triggering. And it will configure the IBE, IEV, ICR registers. More on these in a few moments. Then here we clear any prior interrupts. Here we have unmasked the interrupts. And here we have the, sorry, I was going too fast, enable the NVIC interrupt and set priority for the GPIO, and enable GPIO interrupt here. And then here we have an unconditional branch from here to here. That means this is a infinite loop. And then the GPIO _ handler prog. Now this is the ISR, the interrupt service routine, and it's all here. And then the check P _ PF0 subroutine. And then here is the end of the program. So it's a fairly lengthy program, but not to worry, I will be explaining it to you in a few moments. The program explanation. So here, this part, the beginning part of the program, this is the initialization section. Now, the first line here, area, my code, read only. Area is an assembler directive in ARM assembly language, and is used to define specific area in memory where the code is stored. All right, it's just a directive, assembler directive. My code defines a new code section, and I've called this section my code. Now you can call it any other name. You don't have to be my code. And code indicates that this section contains executable code. And then read-only means the section is read-only and cannot be modified at any time. Here we have the export directive and __ main. This means that this symbol is visible to the linker. And then this is the export GPIO F _ handler, which is the ISR or interrupt service routine. An entry here marks the entry point of the program. Okay, so this section, from this point onwards, this section here defines the symbolic names using the EQU directive or equate. So, so these are the names of given to the registers. So the first one here, SYSCTL_RC_GC_GPIO, that is the system clock control gating control register. All right, so that is the address is 400FE608 hexa. That has been assigned to this symbolic name here. Then we have the GPIO F _ base. That has been assigned this address 400250000. Now this is the GPIO port F base address. Okay, so at this point, I'd like to take a brief look at the SYSCTL_RCGC_GPIO register address and also the GPIO F base address. Here is a list of ports base addresses taken from page 658 to 659 of the datasheet, and I just like to highlight this GPIO port F APB. APB stands for Advanced Peripheral Bus, and so this is GPIO port F base address, which is 40025000 hexa. And this is the general purpose input-output run mode clock gating control, or RCGC GPIO. It has an offset of 608 hexa, and I've taken this diagram from page 340 of the datasheet. As you can see, the RCGC GPIO register is a 32-bit register, and only bit 0 to bit 5 are used, and basically the register provides software the capability to enable and disable GPIO modules in run mode. Now let's take a look at this GPIO F _ lock EQU GPIO F _ base plus 520 hex. Now this is the GPIO port F lock. Now take a look at this one. This has been assigned this value here. All right, so what this actually means here, GPIO F _ base at 520 hexa. What that means is this. So the resultant address is GPIO F _ base, which is this value here, and plus 520 hexa gives us a resultant address of 400 to 5520 hexa. So this, the GPIO f_log would have this address. Now this applies to all these other registers. Now, so this one here, GPIO f_CR, that is the GPIO port F commit register. Then dir here is the direction, and den underscore that is the digital enable. PUR here, this is the pull up select register, and these registers which are highlighted in green, these are all the registers that will be involved with the interrupts. So the first one, IS is interrupt sense, IBE, that is the interrupt both edges, IEV, that's the interrupt event, ICR, that is interrupt clear, IM, that is interrupt mask, and then MIS, the mask interrupt status, and then data is data register. Now, all these we will come across in a few moments. And then here we have the NVIC, PRI7, NVIC underscore ENO, that is the priority 7 register, interrupt set, enable register 0 for ENO, and then the unlock key. This is the key for unlocking the GPIOF. We'll talk more about the unlock key very soon. Okay, so here is the underscore main prop, which marks the start of the main routine. Now, these instructions in the red box, these instructions, basically the purpose of these instructions is to enable the clock to port F by enabling bit 5 of the RCGC GPIO register. All right, so let's look at this instruction here. Those viewers of the channel will be familiar with this. So basically, this will load or copy this into register R0. Now, this we have talked about it because we have declared this or defined this earlier. So the value or the address given is 400FE608 hexa. So that will be copied into register R0, and here we copy whatever that is stored in the address pointed to by R0. Now R0 is pointing to this address. So whatever that is stored here in this address will be copied into register R1. And then the next instruction here, which is a bitwise OR instruction, basically this will set bit 5 to enable port F clock. All right, so this is a bitwise OR operation, and here the store instruction will store the current value of R1, which is it got the value from here. All right, so store the current value in R1 into the address pointed to by R0. R0 is pointing to this address. So whatever the current value in R1 will be stored into this address. Then we come to the next 3 instructions here. Basically, this will unlock port F0. All right, so GPIO F_log we had discussed this earlier. just a quick reminder. Okay, the unlock key, we'll come back to this in a minute. The GPIO f_log, it has got this address. So that address is copied into R0, and then the unlock key. Now this is the value of the unlock key, which is 4C, 4F, 43, 4B hexa. So this will be copied into R1. And then the familiar store instruction here basically will store the current value R1 into the address pointed to by R0. R0 is pointing to this address. Okay, so these instructions here, the purpose of these instructions is to reconfigure port F0 by unlocking it in the GPIO f_CR register. And this GPIO f_CR symbol was been assigned, or has been assigned, this value. All right, remember the address of this is basically the GPIO f base address, which is 400250000 hexa, add the offset of the commit register, CR register. So the resultant address is 400255524 hexa. That is the address or the value that will be copied into or loaded into R0. Now, this instruction here, the MOV instruction or move instruction, will copy this value, hex value 01, or load it into our register R1. And this store instruction will store the current value, which is this value here, into an address pointed to by R0. Next, these instructions here will lock port F again. All right, so let's take a look at this instruction here. If you notice, this is identical to this one up here. So this lock, this GPIO f_lock has this address. All right, that was assigned as the rest of them has been assigned much earlier. So the address, I'll repeat myself, 400255520 hexa. This will be loaded or copied into R0. And then this move instruction will copy this hex value, 00 hex into register R1. And basically, this is the value that will lock the GPIO F. And then here, this store instruction will store the current value of R1 into an address pointed to by R0. And R0 is pointing to this address that will write this value into this address, which is the lock register. Okay, so these instructions here, the purpose of the is to configure PF2 as output, that is port F bit 2 as output, and then PF0 and PF4 as input. And this instruction here basically will load this address. This address, by the way, just a quick reminder, is this address is basically the GPIO base address at 400 hex, and that gives us 4002540 hexa. So this address or this value here would be copied or loaded into our register R0. And this load instruction here will load the current value of the address pointed to by R0. R0, quick reminder, is pointing to here. So it will load the current value here of this address into register R1, and this instruction here, which is a bit clear, BIC is bit clear instruction. Basically, that was set port F bit 4, PF4 as an input, and then this one will clear bit 0, PF0, PF0, set it up as an input, and this ORR, or bitwise OR operation, basically that was set bit 2, PF2, as an output. And then finally, this store instruction here will store the current value of R1, which has been modified up here, store the current value of R1 into the address pointed to by R0. R0 is pointing to this address. And we'll take a quick look at the GPIO direction register, DIR, that we have mentioned here. I've taken this from page 663. This is a quick reminder. Viewers of this channel will have encountered this before, but I will briefly just mention this. It's a 32-bit register, but only 8 bits are used to determine the data direction of the register. And then setting a bit in the GPIO DIR register configures the corresponding pin to be an output, while clearing a bit configures the corresponding pin to be an input. Okay, so these instructions here basically will enable the digital functions for GPIO pins PF0, PF2, and PF4. So quick reminder what this address is. Alright, so basically this is the base address of 4002500 at the offset of the DEN register, which is 51C hexar, giving us 4002551C hexar. So this would be, this address or value will be copied or loaded into register R0. And then here, the load instruction will copy the current value pointed to by R0, which is pointing to this address. Will copy the current contents of this address into register R1. And the next 3 instructions are basically bitwise OR operation, and the purpose is to enable the digital function for port PF4 here, PF4, and then enable the digital function for PF2, all right, and then enable the digital function for PF0, all right. So and then the store instruction here basically will store the current value of R1, all right, into the address pointed to by R0, and R0, quick reminder, is pointing to this address, and that's basically these instructions here, the purpose of these instructions. All right, so let's take a quick look at the GPIO digital enable register. It has an offset of 51C, and as mentioned earlier, I've taken this out from page 683 of the datasheet. It's a 32-bit register, but only these 8 bits are used. So this is the digital enable register, and to use the pin as a digital input or output, either GPIO or alternate function, the corresponding GPIO DEN bit must be set. Okay, so these instructions here will enable the internal pull-up resistor for GPIO pins PF4 and PF0. And a quick reminder what this load instruction do. I'm sure by now you have got the idea. So basically it will load this address 400255510 hexa, all right, into copy that address or this value into register R0, and then here we will copy the current value of the address pointed to by R0. R0 is pointing to this, and the current value of this address will be copied or loaded into register R1. And the next two instructions are basically bitwise OR operation. The first OR instruction here basically enable the pull-up resistor for PF4, and this other OR operation will enable the pull-up resistor for PF0. And this store instruction here will store the current value of R1 into the address pointed to by R0, and R0 is pointing to this address. Let's take a brief look at the GPIO pull-up select register. It has a offset of 510 as mentioned earlier, and I'm taking this thing from page 668 of the data sheet. It's a 32-bit register, but only 8 bits are used. So this is the GPIO pull-up control register. So when a bit is set, that means set to 1, a weak pull-up resistor on the corresponding GPIO signal is enabled. Okay, so this instruction configures the edge sensitivity for interrupt triggering on PF4 and PF0 for falling edge detection. And here we have this load instruction, very familiar to us by now, but let's take a quick look. So this here symbolic name for the interrupt sense register IS has a hex address of 400254404 hexa. So this value or this address is copied or loaded into register R0. And this load instruction here basically will load the current value of the address pointed to by R0, and R0 happens to be pointing to this address. So the contents of this address, the current contents of this address, is loaded into register R0. Now the next two BIC bit clear instruction basically set the edge sensitivity for PF4 and edge sensitive for PF0. So PF4, PF0. So, and the next one, the next instruction, the store instruction, will store the current value of R1 into the address pointed to by R0, and R0 is pointing to this address. And here is the GPIO interrupt sense register. GPIO IS has a offset of 404, and I've taken this diagram from page 664 of the data sheet, and only 8 bits of the 32-bit register is used for the interrupt sense, and then setting a bit in the GPIOS register configures the corresponding pin to detect levels, while clearing a bit, that means setting it to a 0, configures the corresponding pin to detect edges. Right, so these instructions here in fact, if you notice, most of the instructions are similar or almost identical. Now, these instructions here configure the IBE, the IEV, the ICR registers for falling edge. So this one here, the GPIO F_IBE, that's a symbolic name for the interrupt both edges, IBE, interrupt both edges. Now this symbolic name here has this address, which is 400254008 hexa. So that this value is now loaded or copied into register R0. And so LDR load the current value of the address pointed to by R0. Now R0 is pointing to this address. So whatever the current value is in this address will be copied or loaded into R1. Now BIC, that's bit clear instructions. Basically, this disable both edge detection for PF4 port F bit 4 and PF0 port F bit 0. All right, so this is PF4, PF0. And here the store instruction will store the current value that is in R1 into the address pointed to by R0, which is this one here. All right. Let's take a quick look at the interrupt both edges register. GPIO IBE has an offset of 408, and I've taken this from page 665 of the datasheet. Again, very similar to all the other registers. It's 32 bits. However, only 8 bits is used for the IBE. So when the corresponding bit in the GPIO interrupt sense or GPIO IS register is set to detect edges, setting a bit in the GPIO IBE register, which is this one here, configures the corresponding pin to detect both rising and falling edges. Right. So next we come to this group of instructions here, and the purpose of these instructions is to configure the falling edge detection for port F, PF0 and PF4. That is port F bit 4 and port F bit 0. So let's take a look at this instruction here. Basically, this will load the register address of this. This is symbolic name. Let's quickly remind us that is actually 4002500 hexa at 40C. That is the offset for this register, giving us the resulting address 4002540C hexa. So this address or this value will be loaded or copied into R0. And this load instruction here basically will copy the current contents of the address pointed to by R0. Now R0 is pointing to this address. So whatever the current contents of this address will be loaded or copied into register R1. Now the next two instructions are BIC instruction. Basically, quick reminder that is bit clear instruction. So this one here will clear bit 4 of in R1. That is bit 4 corresponding to PF4. All right, and then this one here perform identical operation, except that it is performing is clears bit 0 corresponding to bit 0 in R1, all right, which corresponds to PF0. So these two instructions will clear it and set it for falling edge detection. Then finally, we come to the store instruction. I think by now you would have guessed this will store the current value in R1, copy that value into the address pointed to by R0, and R0 is pointing to this address. And next, we want to take a quick look at the GPIO interrupt event register, which is the one that we've seen earlier. So this GPIO IEV, I've taken this from page 666 of the data sheet. Again, it's 32 bits register, but only 8 bits is used for the IEV. So setting a bit in the GPIO IEV register configures the corresponding pin to detect rising edge or high levels. Clearing a bit, that means setting the bit to 0, configures the pin to detect falling edges, which is what we have done in our code. So all bits are clear by a reset. Hey, so these instructions here, if you look at them, is identical to the previous ones, but let us go through it. So these instructions here, basically the purpose is to clear any pending interrupts for port F pins PF4 and PF0. All right, so here is the familiar load instruction here. This time we're loading this symbolic name whose address is this one here. All right, so this address is assigned to this symbolic name, and this get copied or loaded into R0, register R0, and then this here will copy the current contents of the address, the current contents of the address pointed to by R0, and R0 is pointing to this register which has this address. So whatever the current contents of this address is loaded or copied into register R1. Now the next two instructions are bitwise OR instruction. Basically, it clears, all right, the bit 4 of port F and bit 0 of port F. So these OR instructions here will clear those bits, all right, by setting the bits contradictory, but that's how it works. So this one here will set bit 4 to a 1, and that clears any pending interrupt. Similarly, this is the same here. All right, so bit 0 is set to a 1, which clears all the pending interrupts, okay, for these 2 bits. So it clears the pending interrupts for these 2 bits here. And this store instruction will store the current value of R1 into the address pointed to by R0, which is this address here. And here is the diagram that I've taken up from page 670 of the datasheet. And this is the GPIO interrupt clear, or GPIO ICR. Offset is 41C, which we've seen earlier. And basically for edge detect interrupts, writing a 1 to the IC bit in the GPIO ICR register clears the corresponding bit in the GPIO RIS and the GPIO MIS registers. Okay, so these instructions here, as you notice, is identical to to the one up here. So let me just go through it with you, because this GPIO F underscore IM, the symbolic name for the register, has this address. All right, so it's 40025.410. That's the combination of the GPIO F base address at the offset of this interrupt mask register. So this address or this value will be copied or loaded into register R0. And then from there, this second load instruction will copy the contents of the address pointed to by R0. So R0 is pointing to this address. So the contents of this address will be copied or loaded into register R1. Now, the next two instructions are bitwise OR instruction. Basically, this will set bit 4 of port F to a 1, and this one will set bit 0 of port F to a 1. Basically, the purpose of these two instructions is to unmask the interrupts. All right. So the last instruction here is the store instruction. Basically, that will copy the current value of R1 into the address pointed to by R0, which is pointing to here. Now, this is the GPIO interrupt mask register. Has an offset of 410 as we've seen earlier. So this is the GPIO IM, and I've taken this from page 667. Again, it's a 32-bit register, but only 8 bits are used for the interrupt mask. So setting a bit, I mean set it to a 1, in the GPIO M register allows interrupts that are generated by the corresponding pin to be sent to the interrupt controller. Clearing a bit, that means setting the bit to 0, prevents an interrupt on the corresponding pin from being sent to the interrupt controller. Okay, so these set of instructions here, 1, 2, 3, 4, these 4 instructions here enable the NVIC interrupt and set the priority for GPIO F for port F. All right, so let's quickly go through this. So this here has this address, which was defined earlier. So this address or this value will be loaded or copied into register R0, and then this value 3.3 will be copied or moved into register R1. And here we have an LSL, that is to a shift instruction. This will shift the value in R1 5 bits. Now this is to shift, to set the priority 3. All right, so this is necessary because the priority bits are located at specific locations in this register. All right, so that's the purpose of this instruction. And then we have the store instruction, as most of you will be familiar by now, is to copy the current value of R1 into the address pointed to by R0. And the next 4 instructions here, basically the purpose is to enable the GPIO F interrupt. All right, and this NVIC underscore EN0 register has a address of this value. So this is copied or loaded into register R0, and then this will this load instruction will copy the current value of the address pointed to by R0. R0 is pointed to here, so the current value of this location will be copied or loaded into register R1. And the ORR or bitwise OR operation will set bit 30 to a 1 that will enable the interrupt for GPIO F. All right, and then here the store instruction will store the current value of R1 into the address pointed to by R0. And quick look at the register 36, which is the interrupt 28 to 31 priority PRI7, which have an offset of 41C hexa. I've taken this from page 152 of the data register. Basically, here is the table that shows each register holds 4 priority fields, 1, 2, 3, 4, that are assigned to the interrupts as follows. All right, now this might be a bit confusing. So the first field, bits 5 to 7, which is 3 bits here, that's for interrupt 28. All right, then 13 to 15, that is another 3 bits that is set for priority 29, interrupt 29, and then 21 to 23, that is for interrupt 30, and then 29 to 31, that is for interrupt 31. So 3 bits are assigned for each field. One of this is a field, right? So there are 3 bits in each field. Next, we take a look at the interrupt set enable, EN0, which has an offset of 100 hexa. This is taken from page 142. It's a 32-bit register. Basically, this will enable interrupts and show which interrupt is enabled. And bit 0 of EN0 correspond to interrupt 0. Okay, so we've come to the main loop. So here B, this instruction here is an unconditional branch from here to here. So basically this is an infinite loop. And here is the ENDP marker, the mark of the end of the procedure or prog. Then next part is the GPIOF underscore handler prog. Now this is the GPIOF underscore handler is the ISR, the interrupt service routine. All right, so in Kyle Microvision IDE, this name here, GPIOF underscore handler, is related to the interrupt handling mechanism for the general purpose input-output ports. All right, so this name here, GPIOF underscore handler, is important because it follows the interrupt naming convention required by CMSIS, that is the Cortex Microcontroller Software Interface Standard for all ARM Cortex-M microcontrollers. Now, the startup file in the Kyle Microvision for the TM4C123G microcontroller defines these names. So the startup file in Microvision IDE defines these names. And if you do not use the correct name, the microcontroller will not be able to find your function, and as a result will not able to handle the interrupt correctly. So at this point, I just like to briefly show you what I mean by all that. So in your Kyle Microvision IDE, if you go to your project panel and under device, you will see this startup underscore TM4C123.S, that's for assembler, bracket startup. Now, if you click on it or double click on it, you will get this. All right, you'll see this shown on the this panel here. Now, if you then in this file scroll down, all right, if you scroll down, eventually you come to a point where you will see in line 112 DCD. Now, DCD stands for Defined Constant Data. All right, so we find DCD GPIO F underscore handler, right? That's the one that we've been using in our code. So this is the, so it defines, here it defines the address of the GPIO underscore F handler subroutine, which handles interrupts for the GPIO port F. Right, so we've come to this part again. Now, this instruction here, it looks familiar. It should look familiar to you by now. So this register has been given this. All right, this is the GPIO F base. Add the offset for this register. You will get a resultant address of 400-25418 hexa. All right, this will be copied or loaded into register R0. And this LDR instruction here, basically, that will copy the contents of the address pointed to by R0. Now, R0 is pointing to here, which is this one here. So the contents of this location will be copied or loaded into register R1. And a quick look of the GPIO mask interrupt status register, which had an offset of 418 that we seen earlier. This is taken from page 669. It's a 32-bit register, but only 8 bits are used for the mask interrupt status. So the GPIO MIS register is the mask interrupt status register, as mentioned earlier. If a bit is set in this register, bit set, the corresponding interrupt has triggered an interrupt to the interrupt controller. If a bit is cleared, then bit is 0. Either no interrupt has been generated or the interrupt is masked. And this is the interrupt service routine that checks if the interrupt was caused by the switch SW1 or the PF4, that is port F bit 4. Because SW1, the switch is connected to PF4. Now, this instruction here, TST R1, hash 0x10 is hexa. Now, this instruction here tests if bit 4 of R1 is set. Now, if the bit is set, because this bit here, which is bit 4, correspond to the interrupt pin that is PF4, all right, where the switch is connected. So it will check for the condition or the status of this switch. Then this instruction here, BEQ, check if bit 4 of R1, and if bit 4 is not set, all right, if it's not set, then it will branch to this subroutine. All right, more on this later on. However, if the interrupt was caused by PF4, it will then branch to this, it will then move on to this instruction here. Now, this GPIO F underscore data, that has this address, been given this address, that is basically as a result of the GPIO F base address at 418 hexa, which is the offset of this register, and the resultant address would be 40025.418 hexa. All right, so this will then be copied or loaded into R0. And here, basically, it will copy the contents of the address pointed to by R0, and R0 is pointing to this address. So the current contents of this address will be loaded or copied into R2. And this ORR instruction, which is a bitwise OR instruction, that will set bit 2, all right? Sorry, that will set bit 2 to a 1, and that in effect will turn on the LED connected to PF2. Then here, this store instruction will store the current value of R2 into the address pointed to by R0, and R0 is pointed to here, so whatever the current value in R2 will be stored in that address. Now, this LDR load instruction will copy this address, which is gotten from the GPIO F base address add with the to the address offset, 3F C hexa of this register. So the resulting address would be 40025.3FC. So this address, so this value will be copied into R0. And then the move instruction will just copy this hex value 10 into register R1. Basically, the purpose of this is to clear the interrupt flag for PF4. And then this store instruction here will copy the current value of R1 into the address pointed to by R0. So R0 now is pointing to this address. So the current value here will be copied into this address. And then the BXLR instruction basically will return the control back to the main program. And ENDP here marks the end of this GPIO underscore handler procedure, or ISR. Okay, so let's take a brief look at the GPIO data register. Offset is 000 hexa. I've taken this from page 662 of the datasheet. The GPIO data register is a 32-bit register. Only 8 bits are used. Now, in software mode, values written in the GPIO data register are transferred onto the GPIO port pins. Now, this is the GPIO interrupt clear, or GPIO ICR. Offset is 41C, and you can find this on page 670 of the datasheet. Again, only 8 bits out of the 32 bits are used. And for edge detect interrupts, writing a 1 to the IC bit in the GPIO ICR register clears the corresponding bit in the GPIO RIS and the GPIO MIS registers. And this subroutine is part of the ISR, that is the GPIOF underscore handler discussed earlier. Now, this subroutine checks specifically if the interrupt was caused by PF0 or this actually the SW2 switch. And the test instruction here, this performs a bitwise AND operation between the contents of R1 and this hex value 01. Now, basically the purpose of this is to check if bit 0 of R1 or bit 0 of PF0 is set. Now, if this is set, if bit 0 is set, then it indicates that the interrupt was triggered by the SW2 or PF0. And BEQ done underscore handler, basically if the result of the test is 0, that means which indicates that that PF0 is not the source of the interrupt, the processor will branch to this part here. We'll come to this part later on. And if, however, if the interrupt was caused by PF0, then this instruction, LDR instruction, will be executed. And this GPIOF underscore data, that is been defined earlier with this address. That is basically the GPIOF base address at the offset of this register, the data register. And the final, resultant address is 400253FC. So this hexa, this would be copied into register R0. And then here, the current contents of the address pointed to by R0. R0 currently is pointed to this address. So whatever the contents of this address is, will be copied or loaded into R2. Now, the next instruction, which is the BIC, bit clear instruction, basically the purpose of this is to clear bit 2. All right. So that will turn off the LED connected to PF3. And then here, the STR instruction, the store instruction, will store the current value of R2 into the address pointed to by R0. And R0 currently is pointing, at this point, is pointing to this address. So whatever is in R2 will be copied into this address. And then this load instruction will copy the address assigned to this symbolic name, the ICR. Now that has this address. All right, so this address here, 40025441C, will be copied or loaded into R0. Basically, the purpose of this is to clear the interrupt flag. And then finally, we have copying here, the move will copy this hex value into R1. And then the current, this store instruction here will store or copy the current value of R1 into the address pointed to by R0. And R0 at this point is pointed to this address. And then the BXLR instruction here will return the control back to the main program. And ENDP here marks the end of this subroutine. Now, coming down to this done underscore handler procedure, this subroutine here, basically this here declares the beginning of this subroutine, short subroutine. And in this subroutine, we have a BXLR. So when this branch is taken to this point, this will then return the control back to the main program. So this subroutine could have exit at this point, depending on the test result here. And then this align directive aligns the instruction or data in memory to a certain boundary. All right. And ENDP here marks the end of this short procedure. And finally, END here marks the end of the entire program.
Demonstration. Now for this demonstration, you will need the Tiva C series LaunchPad board connected to your desktop or your laptop. Okay, so here is my Kyle Microvision IDE, and I've uploaded the code here. So let's go through this very briefly. So my initialization section is here. All my definition of the symbols for the registered addresses are here. And then from this point onwards is the beginning part of the main procedure or the main routine, main program. Here, scroll down. If I just go down slowly, and here is the infinite loop. All right, and here is the GPIO underscore handler, the ISR, and is the bit that ends the program. All right, so let me just scroll back up, go to project. I'm going to choose build target, and it says 0 errors and 0 warnings. That's good. Now I'll upload the board. Before I do that, let me just show you my physical setup. Here it is, my board. This is my Tiva C series board connected to my laptop. And just to point out, this is the SW1 push button switch, SW2 push button switch. All right, the blue, the RGB LED is up here somewhere. All right, so it's already it's already compiled. So let me just upload the code to the board. This will go off for a while. All right, let's bring the board back up. All right, let me do a reset, which is here. The reset button is here. And then now if I press SW1, the blue LED should come on. It does. So that's the interrupt. And when I press SW2, the LED should go off. It does. All right, let's do it again one more time. SW1, blue LED comes on. SW2, it goes off. Just one last time. SW1, okay. SW2 goes off. All right, so that's it for this particular demonstration.
Okay, so that's it for this long video. I do hope it has been useful. Thank you for watching, and I'll see you in the next video. Bye.